Okay, welcome back. Welcome back. So we have equations of motion. We've derived the equations of motion for an electric motor. We have an electrical part, so that governs the electrical operation of the motor. And we have the mechanical part, which governs the mechanical part of the motor. And so if we're going to write the electrical equations of motion for this motor, what we did last time is we've got I, R. Well, let's use the Laplace transform. I, R sub m plus L, S, I plus K, E, S theta of the motor is equal to V N. So we've got that. We've got our equation. So that's our electrical equation of motion. We've also got a mechanical equation of motion. It looks something like this. So if we worked on it, this is going to be J equivalent S squared theta out plus B equivalent prime S theta out is equal to Km R2 over R1. That's the motor torque constant times the current I plus D, so whatever disturbance force we have on it. So here's our two equations of motion. And we could solve these equations of motion. So one of the nice things about Laplace transforms is we could combine these equations algebraically. Today what I'd like to do is I'd like to do some block diagram work. And what I kind of want to remind you here is that block diagrams and Simulink are kind of the same things. Simulink diagram. So if you can do block diagrams, you can do Simulink diagrams. And so what I'm going to do is I'm going to look at a Simulink diagram. I'm going to build a Simulink diagram in the form of a block diagram. There's a couple things that are some idiosyncrasies of MATLAB that I'll explain along the way. But the general rule of thumb is to solve for the highest derivative. So the first step is usually to solve for the highest derivative. Now, when I say solve for the highest derivative, like that's going to be in Denver. But okay, well, maybe not. The highest derivative isn't in Denver. It could be in Maine now because they just legalized pot in their state also. So wherever you want to go. The first thing that we're going to find is we're going to see that when we try and solve this equation, the electrical equation for the highest derivative, we see that this has an S theta in it and this has an SI in it. So both of these are the same derivative. But what I'm really looking for, what the electrical part of the motion is really telling me is I'd like to solve for I. I'd like to solve for I. So I'm going to solve this equation this way. LSI is equal to VI minus Rm times I minus Ke S theta m. Okay, so I'm going to solve that equation, and I'm going to end up making a block diagram for that. And so here's my block diagram. Here's what I'm going to do. Let's see. I've got a Vi coming in here. Vi comes in. And I've got a plus on that one. And I guess I'd like to subtract off, at this point in time, I'd like to subtract off a variable that is Ke S theta m. Now I'm going to take that. I'm keeping these two subtraction junctions. They're summing junctions, but they're both subtraction. I'm keeping them separate for a specific purpose. You could put these, even on MATLAB, you could put these together on one thing. So here I'm going to have, this is going to be Rm times I. That's what I'm doing. And if I do that, if I take Rm times I, if I take Vi, I subtract Rm times I, and I subtract Kes theta, then what I get out of this is L, S, I. That's what the variable is. But I'm not interested in LSI, right? I am interested in I. And so what I'm going to do here is I'm going to do 1 over L. That's a block. Now, I'm going to put in here, Simulink, they're crazy, so, I'm just going to say, if you're using Simulink, it has to look like a triangle. That's going to be the last time I say that. They use a triangle, I use blocks, okay? So this is, now, what comes out of here is the variable S times I. Now, I don't want S times I, I'm looking for I. And so what I'm going to do right here is I am going to multiply by 1 over S. If I multiply by 1 over S, that gives me I. That's the current I. Now, you know, I could just go ahead and hook these two together this way. This is going to be Rm times I. And now I finished my block diagram here. Okay, so this is going to be an aside. We're going to have it go to an aside. And what we see in this block diagram, it's important to put your plus and minuses, what they are. So I'm going to look a little bit at block diagram algebra. Okay, so there's an important thing, is that here is a loop. Loops are great. As soon as you see loops, you go, oh, it's a loop. And so what I'm going to do is I'm going to show you in a control system. If you're a control system engineer, you know how the loops work. And here's the way the loops work. The loops work this way. I've got what is called the feed forward, and I'm going to call that G of S. And that goes this way because it's the feed forward. And then I'm going to have something in the back. This is going to be the feedback. And this is H of S. Oops, sorry, I did that. I put the arrow in the wrong direction. That's okay. We're going to fix that. H of S. So H of S is the feedback. It goes this way. And what happens is here's H of S. And then we have a summing junction here. I'm going to call this can either be minus or there's another. You don't have to always be plus. And this one is going to be plus. And this is going to be R. This is the reference signal. And this is C of S is defined as the output. Okay, so you say, oh, look, here's a loop. And if you're a control system guy, these are always G, and this is always H. But if I look at this, a lot of times people will call this the error E. Right here is the error E. And so then I'm going to look at it, I'm going to say, So I can actually tell here that C is equal to E times G. Right? So that's C is equal to E times G. I can also tell you that E is equal to R minus HC. And so if I'm looking for C, I guess I'll substitute in C is equal to R minus HC. Oh, don't do C, don't do G, that's a different thing. R minus HC times G. So I can substitute in a little bit. This is going to be GR minus GHC. You know, I should have been carrying this wrong. So I'm using the minus sign here, but there's another option. It could be plus. Each one of these could be plus. Each one of these could be plus. So if you did a plus there, then you just change that minus sign that I've indicated that way. And so now what I'm going to do is I'm going to take what C is equal to, C times 1 plus GH is equal to G times R. Now, oftentimes I'm looking at the equivalent transfer function, T of S equivalent. That is the output over the input. And for this little loop, the output is C and the input is R. And so I can also put that this way. This is G over 1 plus GH. Okay, again, I didn't carry along my minus sign here, but you know, I'll leave that. You can do that way. And if you care, there's a formula. And so we've done it. Now we've derived the formula, but now we don't have to derive the formula anymore. It is just the feed forward over 1 plus the feed forward times the feedback. Okay, I know I got off the edge there, but that's okay. Feed forward, 1 plus the feed forward times the feedback. That's this equation right here. Feed forward over 1 plus the feed forward times the feedback. So in the most general sense of things, that is how you reduce loops. You can reduce loops. Whenever you see a loop, you go, I see a loop, I'm going to reduce it. Because that's control systems. That's what we guys do, okay? So we've got the equations of motion for the electrical part of the system, and once we have the current, we can also use the mechanical system to figure out that if we have the current, we're going to say R2 over R1. That's the gear ratio, right? Oh, here, let me do that. It doesn't matter. So one of the things, it doesn't really matter what order I put this in. If I have R2, I could swap these two and that'd be fine. So the R2 over R1 is the gear ratio. Gear ratio. And this is the motor torque constant. Okay, so that's the motor torque constant. And when I do that, so when I multiply it, this is the overall. So what this means is this is the overall torque that the motor's supplying. And I might be able to also, just for the heck of it, I'm just going to keep this D in here too. And you'll see that both of those D's are plus. So the D is like the external force. So I add that. The force of the motor plus the external force is what gives me my motive forces. And so once I have my motive forces out here, again, I'm going to solve for the highest order derivative. I've got the inputs. I'm going to subtract off B equivalent prime. That's a plus. I'm going to subtract off a B equivalent prime times S theta out. A B equivalent prime times S theta out. And if I do that, what I get is I get J equivalent S squared theta out. So I get that, but that's not what I really want. And I'm going to go by the same thing that we did here. This is 1 over J equivalent. That's going to give me S squared theta out. And now I'm also going to go over 1 over S. That's going to give me S theta. Now, later we're going to need to know later on we're going to look at what the output position of the motor is. But right now, what I'm going to do is I'm going to say that S times theta, this is omega out. And by that same token, you're going to see over here, this is omega of the motor. Now, those are different, right? So the output shaft goes at a different speed than the motor shaft. They're related by the gear ratio. We know that. And so just for the heck of it here, I guess I can go ahead. I don't know what color I'm using here. So I've got an S theta here. And I'm just going to go ahead and connect that together with a B equivalent prime. You know what? I'm a controls guy. Look here. Here's a loop. Here's a loop that I'm going to do. So I'm going to try and solve this loop for an equivalent overall transfer function. So I can take all of these blocks in this loop here, and I can just replace it with a single block. That's not good either. Okay. So let's see what we're going to do. It's the feed forward. So the equivalent transfer function is the feed forward. That's the formula over 1 plus the feed forward times the feedback. Okay, so let's do that. Feed forward, it's going to be 1 over J equivalent S divided by 1 plus the feed forward times the feedback. So 1 over J equivalent S times B equivalent prime. Now, there's kind of a thing that you do here. Almost always it's better. Like if your high school math teacher wouldn't like you to put fractions down at the bottom. You know, you're not allowed to put fractions in the bottom of a fraction. That ain't good. So I'm going to multiply this by J equivalent S. J equivalent S. And that's going to give me, here, I'm going to write it this way. That's going to give me, I'm going to put it this way. It's going to give me 1 over J equivalent S plus B equivalent. So I can replace this entire block, this whole block, I'm going to circle it now. This whole block can be replaced by this. There's a bunch of different ways that I can even write this thing. I can do it this way. I'm going to do this is going to be 1 over b equivalent prime. All these b equivalents all have primes on them, by the way. You'll see why that is later. This is j equivalent over b equivalent prime s plus 1. Huh. You know what? If I wasn't wasn't looking hard enough, this looks like a first order system. It looks kind of like 1 over b equivalent prime 1 over tau 2 s plus 1, where tau 2 is equal to j equivalent over b equivalent prime. So that's going to be the tau 2 is j equivalent over b equivalent prime. You know, here's another loop over here. I might as well just go ahead and do this loop too, right? That's a loop, baby. We're going to do all the loops we can. I'm going to finish this loop over here. This is going to be the feed forward 1 over ls, the feed forward divided by 1 plus the feed forward times the feedback, which is rm. And I'm just going to do a lot of this reduction here. This is 1 over rm, 1 over tau 1 s plus 1, where tau 1 is equal to L over R. So part of what we have to look at, one of the things is, this is kind of a thing that we do. We mechanical engineers, we never include inductance in our motors, hardly ever. They do in the end. I'll talk about that a little bit later. But oftentimes we say, oh, well, I'm just going to neglect the inductance. The inductance values are usually very small. And in this one, they're also small. And so what I can do is I'm going to redraw, like this whole thing now is kind of a subset. So I'm going to redraw it, and I'm going to talk a little bit about what can happen here. So the first thing is I'm just going to pretend like that the motor speed is 0. So it's at 0, we're going to apply like a step input of the voltage. The motor speed is 0, and then we're going to look real close at what happens to the speed and the current. And for this whole point in time, like, I'm just going to pretend like the motor speed is more or less, I'm going to neglect it. It's not exactly neglectable, but I'm going to do it anyway for the sake of illustration. So what I say is that we have Vn coming in here. We have a series of constants. So it doesn't matter. Not only does it not matter where I put this Km or R1. I could put Km first and R1 second. But also here is an Rm over here that's in this block. So I'm going to replace this block, but I'm going to change some of the order of it. It's 1 over Rm. Right? That's 1 over Rm. Okay, I'm going to put these guys in there too. This is going to be Km times R2 over R1. And then I'm also going to come over here and I'm going to get a hold of this guy here. This is going to be this guy, 1 over B equivalent prime. These are all just constants, right? These are all constants. And we know from one of our homework assignments that when you put constants in it, all that does is makes the dynamic equation, the dynamic response, bigger or smaller. It does not change the dynamic response. Okay, so now I've got this 1 over tau 1 s plus 1. And I've got this, which is 1 over tau 2 s plus 1. And now this is omega of the output. So I'd like to look a little bit closer. Like, these are just constants. I don't even care about these. I'm not going to talk about these anymore at all. But I would like to look at what the time constant, what this looks like in a response situation. So I'm going to look at this one. This is going to be time. And this is going to be output 1. I'm going to put it here, 1. Remember, we've got a step input. I'm going to look at output 1. And then I'm going to look at output 2. So output 1 is going to tell me that I've got some kind of a first order response where this is the time constant tau 1, and this is 4 tau 1. And what is tau 1? Tau 1 is equal to, where is it? Tau 1 is equal to L over R sub m. So if you know what L is, and I'm going to guarantee you L is almost always much, much smaller than it's very small. So this happens really fast. The time constant is really small because L is really small, and this happens really fast. And so now I'm also going to, I'm going to do, here, let me point this one. This guy, that's him. This guy over here, this is time. Then this is out 2. Okay, so I'm going to compare these two things, and this is also no more than a second order response where this is the time constant tau 2. Oops, let's not do it that way. Tau 2. This is the time constant tau 2. And remember, this time constant tau 2, this is like 63%, right? And this is 4 tau 2. That's the settling time. So I can look at both of these things individually, right? And then because when I solve this, I'm going to get something that looks like the form. It's going to be this. It's going to be A1e to the minus t over tau 1 plus A2e to the minus t over tau 2, right? That's what we're going to get. That's going to be the output. The total output's going to look something like that. And I've done those. This is 1, and this is 2 over here. 1 and 2, right? I've got 1 and 2 here. This is 1. This is 2. And now what I'm going to do is I'm going to say, well, wait a minute here. Suppose I draw both of these on the same graph, because there's going to be a plus that goes in between them. When I solve this thing here, there's a plus that goes in between them. It goes in between them. It's like this. And now what I'd like to do is I'd like to put the second one on the same graph, and it looks like this. Can you see that? Okay. So we've got those responses 1 and 2, 1 and 2. And what we're going to see is that typically, I know this is small. This is small because A1 is small. A1 is small when tau 1 is much, much less than tau 2. So that means when the time constant is really fast, that corresponding coefficient is small. And so this time constant is really fast, and this corresponding coefficient is very, very small. And so when I add them together, what I see is that by the time I get to 4 tau 1, that response is completely died out. And the only thing that I'm left with now is the response tau 2. If I still didn't care, I could still go through and I could simulate this. In my system here, I would simulate it, and I would say, oh, I'm going to simulate first. I'm going to simulate this whole business that I did. 1. Simulate this. Two, let L equals 0, simulate, and compare. Okay? Wow, this is a mess. Okay. Because what